All right, we're going to talk next about the pathophysiology of diabetes. Again, this should be review. So if you didn't get a full understanding of it the first time, this is an opportunity to go back and catch that up. The functions of insulin, first of all, the pancreas produces insulin and glucagon. Also produces somatostatin, but we're focusing on insulin and glucagon. So the functions of insulin first. Insulin is produced by or released by the pancreas in response to increasing blood glucose levels. We have multiple mechanisms to maintain blood glucose levels between around 80 and 110 to 120 milligrams per deciliter. That's enough to provide adequate energy for cells, in particular for the neurologic system, but also excessive glucose in the bloodstream begins to damage organs and vessels. So we have to have adequate glucose for our body tissues, but we don't want excess glucose in the bloodstream because it starts to cause damage. So insulin has several functions. It allows glucose to get into the cells for energy. So your body cells cannot function without, they need energy to function as they're supposed to provide whatever type cell or tissue that is. It requires energy at the cellular level. That energy is in the form of glucose. That is the primary and most effective way for your body cells to get energy. So glucose needs to get into the cells. Insulin is a hormone that allows glucose to get through that cell membrane. Okay, so that's the major function of insulin. Remember that we try to maintain homeostasis. Our bodies try to maintain a glucose level within a specific range. So once all of the body tissues have all the glucose they currently need, then additional glucose is stored first as glycogen in the liver and in muscle. Okay, that's called glycogenesis. Okay, glycogenesis, the formation of glycogen. So glycogen is stored in the liver and muscle, and that's a storage form of glucose. So if we need extra glucose at a time when we don't have it available, we can convert that back to glucose. Okay, so that's the second. And the third is that it prevents the mobilization of fat from fat cells. Okay, so insulin attempts to maintain attempts to put glucose into the cells and to store it. Glucagon is released when our blood glucose starts to get lower than that range. So remember, homeostasis, we're trying to maintain that range that's enough to get energy to all of our cells, but not so much that it damages the cells. So glucagon is released when we get out of that range on the lower end, and it converts glycogen to glucose. Okay, so remember the glycogen that the insulin stores that glucose as glycogen. Glucagon converts glycogen to glucose. It also promotes something that's called glycogenolysis, by the way. Glycogenesis is making glycogen. Glycogenolysis is breaking glycogen. It also promotes gluconeogenesis, which is breaking down amino acids for glucose. So glucagon is we don't have enough glucose for our tissues, especially the brain. And so we've got to get some sugar in the blood now. That's its purpose. So it converts glycogen to glucose, breaks down that glycogen, and it promotes breaking down amino acids for glucose. It also reduces the amount of glucose that the liver is using. So all of those have the function of raising the blood sugar. So these, remember that hormones tend to work on some type of feedback loop. Blood sugar gets high, we release insulin that moves sugar into the cells and some of it into storage. Blood sugar gets low, we release glucagon, which breaks down glycogen and amino acids. Okay. Now, in type 1 diabetes, if there is zero insulin, then zero glucose can get into the cells. So the glucose that can't get into the cell stays in the bloodstream. So we've got two different things going on. We tend to focus on the high blood sugar and the damage that that's causing, but there's also another thing happening at that same time. If the glucose can't get into the cells, the cellular energy needs are not met. That patient is going to be hungry, polyphagia. They're going to be very tired and weak because no matter what they eat, their cells cannot get energy. Their body is in starvation mode. They will actually start to break down muscle and break down fat, so they may lose weight. Proteins are broken down and converted to glucose by the liver, okay, gluconeogenesis, but we still can't use that glucose because there's no insulin. The tissues say we're starving, we need more glucose. Protein is broken down and converted to glucose by the liver. We still can't use that. Blood sugar gets even higher and still no energy needs being met. Fat is broken down for energy, or lipids are broken down for energy. That actually works to provide some energy for cells. It's very inefficient and it produces a byproduct of ketone bodies. Ketone bodies are acidic, okay? So we have acidotic blood. So remember pH, this is another homeostasis lecture. Remember when Ms. Durant talked about pH? If your pH gets out of range very much, we have mechanisms to try to get it back into range. So if it's a metabolic reason that our pH is low, like we've got too many ketone bodies running around, the body cannot eliminate those ketone bodies fast enough. Kidneys can't eliminate them fast enough. So we eliminate a different acid, and that is carbon dioxide. So that patient may have Kussmaul respirations. And some of you, I know in my clinical, have been able to see that in DKA, that patient's going to have Kussmaul respirations. They're acidotic, can't get rid of the ketones, at least not fast enough. So they get rid of carbon dioxide. And if you do ABGs on that patient, their carbon dioxide level is going to be very low because they're blowing off all their CO2, trying to get their pH back up where it belongs. Okay, so all of that is the energy side of things. All of that is one problem. The other problem is that the glucose in the blood vessels causes some complications. So if I add a lot of sugar to a solution, I make that solution more concentrated, right? Okay, we're going to bring in another homeostasis lecture from last semester, fluid and electrolytes. Ms. Durant taught you about fluid and electrolytes and about osmosis. Water tends to move across a membrane. If a membrane is permeable to water but not to solutes, water will move across that membrane to equalize the solute load. Okay, so if we put a lot more solute in the bloodstream, water, okay, sugar, the glucose in the bloodstream is a lot more solute in the bloodstream. So the water from the cells moves out into the bloodstream. So their cells dehydrate, water goes into the bloodstream. The kidneys cannot retain excessive glucose. The kidneys don't normally eliminate glucose, but again, another homeostasis mechanism. Glucose, if the glucose level is high enough, it can get through that glomerular membrane. But when it goes, water goes with it because the water is still following the solute load. So they have polyuria. So they get progressively more dehydrated. And until they're very, very dehydrated, they'll still have polyuria. They'll be dehydrated and making a lot of urine. We connect dehydration with low urine output. If someone has a very high blood glucose, they'll continue to have high urine output as long as they have the water to eliminate, even though they're dehydrated. So the cells are dehydrated, water's moving from the cells to the bloodstream, and then the glucose goes to the kidneys, water moves from the bloodstream to the kidneys, so it's eliminated. Polyuria, they're very dehydrated, they're very thirsty, polydipsia. So the three cardinal signs of type 1 diabetes are polyphagia, polyuria, polydipsia. Okay. Now, one of the other things that happens with insulin is that it also allows potassium to move into those cells, or affects potassium movement in and out of cells. So if there's no insulin, the potassium's moving out into the bloodstream, and the kidneys, serum potassium level is high. The kidneys recognize that, again, homeostasis, and try to eliminate that excess potassium. So serum potassium may be high when that patient is in DKA, but their total body potassium is low. So we don't want to try to eliminate the potassium. What we want to do is try to get the potassium back into the cells where it belongs. Okay, so all that's going on. Also, that glucose that's sitting in the bloodstream damages body tissues. It damages, in particular, the blood vessels and the nerves. Okay, so we're going to come back to that in a bit. Now let's switch over to type 2 diabetes and pathophysiology. Someone with type 2 diabetes has a pancreas that still works some. So they produce some insulin. So they have decreased insulin levels, but their tissues also don't really recognize the insulin. They're, the insulin knocks on the door to bring the glucose in. The body cells are sitting there with the curtains pulled and not answering the door. Okay. So insulin, the tissues become resistant to insulin. So it takes more insulin to get glucose into the cells, and they're probably producing less. So some glucose gets into the cells, but it's not enough to meet their body's metabolic needs. It is enough to usually prevent breakdown of lipids. So their energy needs are not completely met. They're fatigued. They may be hungry. They may gain weight. Remember, we lose weight with type 1 often, but type 2, they may gain more weight because they're able to they have some insulin. So they're able to do something with that glucose, even if the cells don't want it. Proteins broken down and converted to glucose, that further increases glucose levels, but we don't use it any better. Okay. Fat breakdown is less likely. It is still possible. You will still see someone with type 2 diabetes occasionally in DKA. More often, they're in something called HHNS, hyperglycemic hyperosmolar nonketosis, or nonketotic state. And we'll talk about that in a bit. So blood glucose increases. Again, water moves out of the cells into the bloodstream to even out that balance. And then the glucose leaves through the kidneys because it's too much. Water goes with it. So still have polyuria and polydipsia. Okay, they're dehydrated, they're thirsty. Potassium moves just the same way. Potassium moves out of the cells into the bloodstream, and then it's lost in the urine because the kidneys think there's too much. And again, the serum potassium may be high and the total potassium low. With type 2, the onset tends to be more gradual. Type 1 tends to be sudden. They have a viral illness, a few days or weeks later, their pancreas just quits. Okay, so they go from insulin to no insulin. With type 2, the onset tends to be more gradual most of the time, which means their symptoms have a more gradual onset. They're not as noticeable. They can get much, much more dehydrated. The dehydration can become more severe with type 2. Because it's a gradual progression. Okay, in the next section, we're going to talk about diagnosis, and then we'll talk about management. And we'll come back to that pathophysiology and talk about complications in a little while.